Okay, so in this presentation, I will cover the work that we are performing in the ArtIAMAS CA in Project 2.3. So this is going to be more relevant to the ArtIAMAS itself. So while we have some results that I'll present today, some of the work is still ongoing. So I'd like to acknowledge my students, Nelson, Rohan, and Preetham, who have done most of the implementations. Not 100%, some of it I've done myself, but most of the implementations, and also some of the research ideas. So they definitely deserve full credit. Also, our aerial colleagues, Dr. Carl Bussard and Robert Ebacker, on a weekly basis, they have given us a lot of directions, ideas, thoughts, suggestions, and things like that, which have been incorporated into this research. And then from colleagues from UMBC, Anupam Joshi and Team Finein, and from College Park, Dr. Rajiv Burra. Okay, so my presentation is going to consist of three main topics. How do you detect attacks? By training machine learning models that can cut across domains. And by domains, I mean attack types, operating systems, operating environments, and things like that. And here, I'll focus on two types of defenses. One is two types of attacks and defenses against those attacks, both network-based and host-based intrusion detection. The second one is model poisoning attacks that are usually done in Federated Learning, and there is some overlap with A2I2, but we're actually building on a lot more research ideas. And the third one is data poisoning attacks. Now, we will be discussing mainly data poisoning attacks that can be launched by changing environmental factors. This is slightly different from current research in this area because the current research makes a strong assumption that the attacker has been able to infiltrate into the system and gone undetected for a length of time, which can happen. But in our case, we are actually talking about attacks that require no such infiltration whatsoever. So we are going to present how Army assets and tactical information can be secured using a three-tier architecture. So I'm going to start with the bottom tier, which represents backend servers that train deep learning models with large amounts of data that will subsequently be pushed to the edge for inferencing. We will demonstrate how adaptive models for detecting and preventing various types of attacks can be done at this level. So the middle tier represents base stations that collect data from various edge devices that are mounted in UAVs, UGVs, and things like that, and then fine-tune the AI models based on new information. This also covers cyber defense in federated learning environments where the nodes are kind of doing their own training and then sending updates to a parameter. It's also called master node sometimes. I'll give you a lot more details on that in the coming slides. And then the top tier represents the front ends where autonomous sensing and inferencing is done through AI models. And we'll illustrate how to build resilient models to defend against data poisoning attacks at that level. Okay, so I'll start with the domain adaptation and generalization. So the main challenge of domain adaptation, which means that you can train the model in one setting and apply it in another, is the fact that one of the basic assumptions in machine learning, which is also true for deep learning, is that the training and test data have the same feature space and follow the same distributions. So if you train a model in one domain, which is typically called the source domain, and apply it in a different domain, call it a target domain, without any fine-tuning, it will lead to performance degradation, massive performance degradation, which has been shown by us and other researchers in prior work. So how do we overcome that? And what is wrong with the current state of the art? Most of the current state of the art are intrusion detection systems that use coarse-grained filters. These may not be able to detect subtle attacks. For example, I talked to a senior cybersecurity engineer from Morgan Stanley, and he said that their IDSs catch a few million suspected intrusions per week. However, what they don't know is how many actually get through. So if those that are based on intrusion prevention systems using machine learning are slightly better, but they still suffer from scarcity of label data, which is a problem across the board. Also, since machine learning is based on, they're trained using previous attacks, if an attack is a completely new attack, for example, a zero-day attack, then it's going to be very difficult to detect them. So this first research is actually a little bit dated, maybe a few years back, but let me start with that, and then I'll go into more current research. So here, what we did was we were able to demonstrate that deep learning models trained in a source domain can be adapted to a target domain with some additional training. This saves a training time and also cost of gathering labeled data, both of which are bottlenecks in deep learning. So the data that we were obtained from the Canadian Institute for Cybersecurity. It is a synthetic data, but realistic, and the data set has been used extensively by many universities, industries, and government agencies. So the figure at the top shows how the data was simulated. So they used an attack network and a victim network. The victim network has 3 servers, a firewall, 2 switches, and 10 PCs. And the attack network has 1 router, a switch, and 4 PCs. And the attacks were generated, both attack and normal traffic were generated over several weeks. And the total number of network traffic data is about over 70 million. And they contain both benign traffic as well as malicious traffic. Some of them are a little bit skewed, some of them are balanced. So we trained a deep learning model for attack detection using one type of attack, in this case, port scan, and tested it against other types of attacks with some fine-tuning. The results are shown in the bottom, and it shows that with about 20% additional training, models built on detecting one type of attack, in this case, port scan, can be adapted to detecting other types of attacks such as botnets, DDoS, infiltration, etc., with high accuracies. So subsequent research in this area has corroborated this idea. So it is not brand new anymore, but this actually shows the feasibility of adaptation. Okay, now I'm going to transition to what we refer to as host-based attacks. In fact, in cybersecurity, this is the term that is used. So the idea is that an attacker is either an insider attack or the attacker has already gained access to the system, which is inevitable. Almost every system is vulnerable to infiltration. So the question is, can we detect attacks, host-based attacks, when the attacker is already infiltrated into the system by analyzing their behavior patterns? So this is not a very well-researched field. The closest research that we have found was published in October 2021. And what they have done is they generated normal behavior using baseline traces for various types of operations like FTP, SSH, modifying configuration files, web traffic generation, downloading files, compiling and executing programs with disk IOs and computation and things like that. So a whole bunch of things that will be reflected in some ways as bash commands or system calls. And the question is, can we take a trace, which could be thousands of system calls and other types of events, and say whether it's whether it's an attack or not? Okay, so what they did was, Ring et al. 2021, is that they using this model, they actually generated the probability that a trace is abnormal using a preset threshold in terms of the number of suspicious system calls. Then they also detect probability of a program being anomalous based on the medians of the traces, median value of the traces. However, they haven't really done anything with domain adaptation, and so it remains an open challenge. So what we have done is we have developed a domain adaptive HIDS, host-based intrusion detection, by analyzing the traces directly. We also created a scoring mechanism, which could be quite useful. If you have got multiple source domain models, then which one is the most appropriate can be answered by using this scoring mechanism. And then a best set of features that could be used. So, so the data, this one shows the number of host-based attacks with known vulnerabilities and weaknesses. So that's why you see the CVEs, the common vulnerabilities and exposure number, and the CWEs, common weakness enumerations, which are done by MITRE. So these are known attacks, some of which are, viruses and things like that. Others are essentially attacks that are already known. Now the data set was obtained from the University of Leipzig. So these are common public domain data sets. But the data set is skewed towards benign traces. As you can see, about 10% of the data set of the traces and attacks, and 90% are benign. So we applied class weight adjustments to make sure that we are able to detect attacks and not just the benign data. So the first thing we did, and this work, by the way, is done by Nelson. I don't know if he's here or not, but so the first thing we did was we created a separate deep learning model for each type of attack and tested the performance with a 25% whole lot sample. So there are two attack types, CVE 2014 and CWE 307, that did not perform very well. As you can see from the F2 score here, and this one is, the F2 score is not so bad, but the precision was pretty bad. So we decided that these two are not very good models. The reason that we did this was to make sure that if an in-domain model is not performing very well, then there's no point in using that to detect an attack in a target domain. And LID is actually combines all of the data sets below. Okay. So now this one actually shows the principle behind model selection in a new domain, or if you're evaluating a new trace as a potential cyber attack. So we first select only those models, as I just said, that have got good in-domain performance. Then we create a domain similarity score. How do we do that? We first create a TF-IDF measure for all the system calls, then create a document vector. A document is essentially one attack type, and then simply take the cosine similarities between the document vectors and the new attack, the new trace that we're trying to decide whether it's an attack or not. So here, the rows are the source domains and the targets indicate the target domain. So essentially for any particular attack type, just go down the rows and see which one gives us the best similarity score. Of course, the diagonals are 1 because they're the same. Okay. Now, we actually did some experiments with these, but they are still not conclusive, so I'm not presenting that just yet. But it seems like they are quite promising in the sense that even in attack cases where the data set is not strong enough in terms of giving good performance, it is possible to actually use data sets from another domain and improve the performance of those types of attacks where in-domain performance is not very strong. Okay, but this one actually shows something that is interesting, which is that if we retrain a model that has been trained in a source domain and apply that in a target domain with some amount of retraining, what is the minimum that we can get away with in terms of retraining? So as you can see, it ranged from 5% to 35%. Even with 5% retraining in the target domain, we are able to generate or achieve about 70%, a little over 71% accuracy. And with 35%, we can reach nearly 85% accuracy. So this again establishes the fact that even in the host-based intrusion detection, this is a feasible strategy. Okay. Now I'm going to transition to federated learning, which is really the second tier, and which is why you'll see that. So the color coding should let you know which tier we're talking about. Okay. So in this particular setup, the model is either built or fine-tuned using multiple nodes at a large scale. There could be thousands of nodes in a distributed fashion. So this work is actually synergistic with the A2I2 project called Scramble, which was presented, I think, in October this year by Saurabh Bagchi from UT Austin, I believe. Our approach is less heuristic than theirs, and we can also identify the compromise nodes which they haven't done. So we are going to compare our results with theirs as to see if we do better than them. But we are able to do a little bit more than them in terms of identifying information, such as which nodes have been compromised, and we also study the effects of collusion. If multiple nodes collude together, what happens then? And also random versus targeted attacks. And I'll talk a little bit about random versus targeted attacks in the next few slides. Existing methods in federated learning, adversarial federated learning, is where they assume that the attacks are completely random, but that is not necessarily going to be the case. Now, the system consists of multiple edge devices, which are in some, mounted in some UAV or UGV. And then there's a FL server, Federated Learning Server, which is also called the parameter server of the master node. So all edges or edge devices are training deep learning models with the same architecture. That is the assumption. At the beginning, the FL server sends an initial model or parameters to all edge devices. So the architecture is the same, but the initial parameters are usually random. So the random is a starting point. And not completely, but more or less. Then the model is trained or fine-tuned using the data residing on each edge, right? So the data is not sent over the network, which means that this saves a lot of bandwidth and possible interception attack that can actually sniff into the data itself. So the data is not shared. So what is shared? What is shared are usually the updates, the gradients, or the weights themselves at each round. So this goes for round, multiple rounds until it is converged. Now, the thing is that some of the edges can be compromised. So a compromised node can send wrong values so that the global model does not converge. And if an FL server actually doesn't know whether if an edge device is a friend or a foe, so there's no way of knowing that unless you do some analysis, which is what we're going to show next. So at each round, the FL server randomly selects a subset of edge devices, m out of n, but m could be equal to n also. Then an edge node updates the model. Each edge node updates the model using only local data and sends the update back to the FL server. The updates could be either the gradients or the weights. The FL server incorporates these updates and the process continues, the round continues. Now this theta is actually n over m, but when n equals m, it's 1 over n. So this is the way that the aggregation is normally done, but this is not the only way to do it. So I'll talk a little bit about those. So if an edge node is compromised by the adversary, wrong data can be transmitted, leading to performance degradation. Okay? And we'll show you some results in a few slides. The FL data does not divulge the aggregation method or which nodes they trust. And the FL server, we are assuming, is protected by security protocols and HIDs and NIDs, so they cannot be compromised. So that is the one assumption that we're making here. Okay, before we should go through the actual methods, let us first look at some sample data. So, for example, here, some subtle changes can lead to drastic performance degradation. In this particular image, for instance, with a slight perturbation, you might be able to see this sticker at the bottom of the stop sign, which makes a deep learning model thinks that it is a speed limit sign with a 95% confidence. Obviously, this will be a bad result if they don't. This is what happens. So in these images, we are showing that with a little bit of perturbation, which might or might not be visible, it is possible to mislead a deep learning model pretty drastically. It will lead to a drastic misclassification error. Now, there are even more subtle attacks that can be done, and those are some of them are shown here. For example, deep learning models typically misclassifies certain images in this particular example naturally. So there is no attack that needs to be done. There are natural mistakes that take place. For example, here it is predicting that this is the picture of a ship, whereas it's a picture of an automobile. This one thinks it's a bird just because there's a rider on top of a horse. This one thinks that this truck is an airplane because of some objects, maybe trees or other buildings on its side. So these are naturally occurring mistakes that a deep learning model is likely to make. And these types of mistakes can be exploited by the adversary very effectively, where it would be almost impossible to detect these types of attacks. These are sometimes known as or referred to as backdoor attacks. Okay, so federated learning requires some communication overhead due to update sharing at each round. Also, the non-IID assumption in machine learning may not be valid in federated learning, which means that it can lead to parameter divergence. So it may not converge very easily. So our goal is to detect backdoor attacks. We cannot prevent backdoor attacks from happening, but we can certainly detect them. Now, our premise is that the parameters in a compromised node will have different statistical properties than those in regular nodes. We think it's a valid premise because otherwise the attacks will fail anyway. If they are not statistically different, the attacks are not going to succeed. They'll not have any impact on the machine learning model. Now, in general, there are two types of attacks that are possible. One is called, two types of updates that are possible. One is model-based, where the weights are shared, and the other one is where the gradients are shared. And of course, the gradients are the loss function is actually minimized by taking the derivative of the gradient with the weights and minimizing it. Now, federated learning is federated averaging. So this is a naive method of aggregation, which means that they take all the updates and just take the average. This is what I showed in a few slides back. It's very simple, but it is not fault tolerant, which is why it's called naive, because a little bit of an outlier will actually throw it off completely. Now, there are other types of aggregation methods that are called Byzantine robust aggregation. For example, median is one of them. Of course, median is not so easy to skew because one outlier is not going to make a difference. However, collision among the nodes can actually make it very feasible to attack median-based aggregation. There are others like trim mean, crumb, Boolean, or Boolean, and flip score and reputation score. All of these have actually known attacks. So now these are very robust. Now, these are things that we are proposing. This I haven't seen in the literature so far. So the question is, what if some of the compromise nodes collude with each other? So we look at three different possibilities. One is where there is no collision. So in no collision, each adversarial node is simply perturbing the parameters independently of each other. In partial collision, the adversarial nodes are coordinating with each other, but they're not saying the exact same updates in each round. Okay? And in the perfect collision, they're totally in sync, and so therefore they're going to send the same update in each round, and this will overcome some of the defense strategies mentioned in the last slide, including the median. Anything that is based on median will be completely overcome. And then there are a couple of perturbation models that we are studying. One is where the adversary wants to prevent the model from converging, and this is the random perturbation. This is the one that is prevalent in the federated learning environment. Now, we are also interested in looking at targeted perturbation. Here, the adversary wants the model to converge, but wants the model to converge to a wrong conclusion. So that will lead to misclassification, essentially. So they are misleading the model completely. So some of the differences of our work with others. So most of the current work uses stochastic gradient descent. updates. And this has been shown to be vulnerable to Byzantine attacks. The other thing that we also want to have a unified methods for all parameters, because deep learning models typically have a large set of parameters. So the thing is that we have to find a way to easily identify which nodes are attacking, which updates are actual attacks and things like that. I'll give you some ideas of what I mean by that in a few slides. Okay, so so early layers are actually agnostic to Byzantine attacks. Why? Because the early layers they learn primitives. For example, for images, they learn colors, lines, texture, and things like that. So attacking or perturbing early layers will not have much of an impact on the model performance. And the other thing I've just said that since deep learning models have very large sets of parameters, we want a unified model instead of evaluating each parameter separately. If you try to evaluate each parameter separately, that's a lot of work, but that is what predominantly is done in the current approaches. Okay, so here, the adversary is using a different set of images to create the parameter space instead of using random values. So this one shows the real data. We are trying to identify army assets, for instance. So 3 classes, and of course, it can be more than 3 classes. And this is the MNIST image, which are the 0 through 9. We are just randomly picking any 3 of these images. So what the adversary is doing is they are training the model using MNIST data and trying to send the parameters over to the FFL server, whereas the regular nodes are trying to train the model using the actual data, which are shown here. Okay, so we have used in our experiments the last flattened layer just before the softmax layer, because the initial layers of the images will not have a lot of impact, but we need to test some of the other layers also in the future. Okay, so this one shows the results. The columns are the percentages of the nodes. So for example, here, so there are 15 nodes, out of which 3 of them are Byzantine nodes. So that's a 20% perturbation. 20% of the nodes are adversarial nodes. In this column, 5 out of 15, which is about a third of the nodes are compromised or are adversarial nodes. And these are none of the nodes are, so 0 perturbation. Okay, now if you look at this particular column, you'll see that the accuracy, so these are accuracies, these are losses. Okay, the accuracies are converging very nicely, right? Something like this. The losses are going down. If you look at the other 2 columns, you'll see that there is really no pattern. So, there is really no pattern, and so therefore it is not converging at all. And this is exactly what the adversary would want to have or want to create, so that the model doesn't converge. Or in the worst case, the model converges to wrong results. Okay, so now the question is, if we were to take the parameter vector, the flattened parameter vector just before the last layer, and plot them and just cluster them into 2 clusters. Why 2 clusters? Because one cluster is for compromise nodes, the other cluster is for regular nodes. Would we see any patterns? Would we see any well-formed clusters? Okay, so, and as you can see, there are 2 clusters that are forming pretty clearly. So the blue clusters are the compromised nodes, and the green clusters are uncompromised nodes, regular nodes. And these are plotted against the 3 classes that we have talked about in the last slide. Now, this separation is possible, and there is very little misclustering. So for example, about less than 2%, about 2% of the data are put in a wrong cluster. However, this particular chart does not tell us which nodes have been compromised. So that's why in this chart, we actually plotted the distribution of the model parameters. And once we do that, you can easily identify the Byzantine nodes. There are 3 of them here, and because they show a completely distinct pattern. Now, one might say, what if the adversary tries to make them closer and closer to the non-compromised patterns? If they do that, and we have to run the experiments to see, their attack is not going to be very effective. So that will most likely fail. So now I'm going to switch gears again and go towards the front end, which is the data poisoning attacks and how do we build resilience against those. So here, the attacker is targeting the front-end devices. Okay, so data poisoning attack is a very well-known attack where the data can be poisoned either at the time of model training or at inferencing. Now, if you do it at the model training time, then the attacker has to be inside the system, which is not easy to do. However, that is what is actually studied in the literature. So this one shows that it's a hyperplane. In this particular case, it's just a line that is separating blues from the reds, right? So these are two different classes, just a binary classification problem. And it's doing a pretty nice job, not 100%, but very nice, very, very, very close. However, if we add some perturbations, some outliers into the data set, all of a sudden the hyperplane changes. Okay, now this doesn't do such a good job, and the parameter vector theta also changes its direction. If this is our hyperplane, then the error is going to be close to 50%, maybe more, I don't know. Because it's going to say anything above is blue, anything below is red, or something like that. No matter which way you do it, it's going to have a very large error. Now, if you discard the outliers somehow, if you're able to remove them, then it comes back to the original plane, right? So after sanitization, we are back to the original performance. Now this one shows a pseudocode for anomaly detection, outlier detection, using L2 vector. So this is called L2 defense, which is a very standard method. It says that take the Euclidean distance and remove everything that is away from the norm. And that's how we sanitize the data set. And then using the sanitized data set, you train your model. Now, this year, I showed a couple of slides back. These are examples of attacks against L2 defense. These types of attacks that are naturally occurring and very close to the original images, as far as the machine learning model is concerned, will not work if you just use L2 defense. And I'll show you some additional results soon. So as expected, errors will increase with the injection of poison data when they're used for training. So depending on what percentage of the training data is poisoned, you can see a huge amount of error getting into the classification models. Now this one shows that if an anomaly-based method is used to identify and remove poison data, it may, so we say that the removal budget is about 25% more than the poison images. So what happens now if you try to remove the poison? You will see that most of the images, most of the data that is being removed are clean data, and only a small percentage of the poison data is actually removed. So the L2 defense is not going to work because this will actually make the data set worse than it was before. So something needs to be done about this. Okay, so now in order to inject poison data at the time of training, particularly, the attacker must be able to infiltrate into the system and remain undetected for a long period of time. Now, we think it is unrealistic. It is very difficult to do that, although it is not completely impossible. But if the system is protected, then it's going to be very difficult to do that. However, there is a much easier data poisoning attack that can be launched at the inference time by simply changing the environment. And this is a very common attack strategy that has not been very well researched in academic literature. In the academic literature, they make mostly the strong assumption that the enemy or the attacker is already inside the system. Okay, now this one shows that how to do object detection using an edge device. This is actually done right here. This is a setup that we've used. This is a Jetson Xavier AGX. And we just did object detection using a pre-trained network, which is an SSD mobile net version 2. which was trained with a 90-class Microsoft Foco data set. And as you can see, it is able to detect, people and the airplane, which are partially, overlapping with a pretty high degree of accuracy. So it thinks that this is an airplane with 93%, close to 93% accuracy. And then it identifies the 3 people in front of the airplane with a high degree of accuracy as well. That's good. But when there is a lot of snow in the environment, then the object detection algorithm's performance deteriorates significantly. For example, it is no longer able to detect the plane. This is undetected. Not able to detect this person, and the confidence of detecting a person goes down from upper 80% to low 50%. So this is a problem. Now this one shows what happens if the objects are covered by dense smoke. So there is some foreground obfuscation or camouflage in a jungle or in a desert. Now we actually created these data sets by using neural style transfer because very difficult to collect objects or images like this. But we are also going to show you some more realistic images that might happen. However, with in these types of situations, when there is a foreground of obfuscation or background camouflage, the objects are undetected, completely undetected by the same model that we used before. Now, we are building object detection models where the objects are camouflaged using background, environment, and vice versa. And as you can see, we are able to detect the soldiers that are camouflaged in the background. And this work, by the way, is being done by Rohan. So these are some more examples of where, you can see that in a snowy environment, sometimes they're completely, hidden, and yet the model is able to detect the objects quite clearly. Okay, so let me just run a video, and how much time? So as you can see, so this is a video that was downloaded from the internet, and then we ran the object detection model in real time, and it is doing about 25 frames per second, but can be much faster than that. So the idea is to capture videos in real time and detect objects autonomously using an edge device mounted either on a UGV or a UV. So the video, as I said, is taken off the internet, and we ran our object detection algorithm where objects are detected, are in the clear, or can be camouflaged to a certain extent. Now, there are only 3 types of objects that are being detected here, but we can extend them more. This can be put either in an unmanned vehicle or a manned vehicle and run on an edge device such as the Jetson Nano or Xavier. So what we are doing is we are starting this further with more camouflaged object detection in the future. I think that's the last slide that I have. So let me stop there and see if there are any questions.
Okay.
I've gone for a while, but I'm open to questions now.
Thank you, Aryya, for your excellent talk. Very interesting talk. Questions from the audience. So, okay, while we wait for questions from the audience, Aryya, I have a quick question. So regarding your the first part of your work, the domain adaptation. So I'm just thinking like you have different types of attacks. So that's one aspect of the heterogeneity. Any other heterogeneity you have been looking into, like traffic, signal of the traffic, or the sources of the network traffic, or any other you can think of?
Yes, we are also looking into different operating systems. For example, different versions of Linux versus Windows, and things like that. So that's another one that we have looked at. The challenge is to really find data. So we are interested in looking into attacks in different environments because the attacker might have a different strategy depending on what type of environment it is actually operating in or trying to attack. So far we have looked at different types of attacks and different operating systems.
Okay, thank you, Aryya. Any other questions from anyone? Okay, I have a couple of more questions. Aryya, my next question is, like you talk about some specific attacks, CVB 2014. So when you ran your experimentation, like in the source and target domain, did you keep the same type of attack, or did you run experimentation with different types of attacks in source and target domain?
Yeah, that's a great question. We ran so the source domain and the target domain are different. So what we did was we first identified. So for example, if you have got n models, right? You have already trained n models in n domains, and now you suspect or you want to determine whether a particular incoming trace is an attack or not. How do you do that? So the first thing is to see which one would be the best model to actually utilize, right? So that's why we have this model selection step, which is essentially looking at the system calls and see how much overlap they have. But then then you can select an attack, a model that is the closest in terms of system call similarities, and then use that to identify whether the attack is, whether the incoming trace or the incoming application or program is an attack or not. So yes, we are, obviously, if there's a lot of overlap in terms of system calls, the accuracy is going to be higher, is expected to be higher. So if this feature space doesn't, the intersection of the two feature spaces is not very large, then we think that it's going to need a little bit more fine tuning in that particular space. If the intersection is very large, then I think it'll do a lot better, a much better job.
Right.
We're still running the experiments, but our initial results, which I didn't present, are actually quite promising.
Okay. Thank you. Thank you.
I had also one quick question, Nirmali. Is it okay?
Go ahead, Tinus.
Yes. Aryya, great talk. I learned a lot. I have actually a very naive question. So about detecting the attack, for example, from your last book that you were just showing about the object detection was identifying the plane and the people, but it couldn't detect it during the snow with a higher confidence and accuracy. Can we also see this problem as a noise problem? For example, just do some pre-processing.
Yes.
You're breaking up, Tinus, a little bit.
Oh, am I breaking up?
Last part of your question.
Oh, can we use this can we again from a signal processing person, can we look at this problem as a kind of a pre-processing stage? When there is a snow, we do some pre-processing to remove the noise.
Yes, I think that is possible. However, if they are, so you can do foreground correction, right? And I'm not sure if signal processing will actually work if the if the entire obfuscation is in the foreground, then you may be able to take them out. But off the top of your head, you don't know exactly what type of obfuscation is happening, right?
Yes, exactly.
Because image wide, I mean, there may be a lot of obfuscation, and the object might be a very small part of the image. So, which is a signal, which is a noise, is difficult to detect, to determine, without any additional information. The other thing is, if in case of camouflage, it's going to be even harder. The reason for that is, they are properly done camouflage is where the background environment and the foreground object are indistinguishable. And people have studied this problem in the animal world, the predators and prey situation. So, I mean, it is very difficult to detect even by the human eye. So, I haven't seen any signal processing work that have actually tried to remove either the obfuscation or the camouflage effect. So what is done is using depth maps, you can do a better job of identifying the underlying object. Right? So for example, the object might be hidden behind leaves, right? So in such a case, the depth map will actually identify the object, even though it is completely covered by leaves in front. But so to answer your question, I haven't really seen any studies that have tried signal processing, but it might be a viable method to try.
Thank you very much. That was actually very helpful.
Sure.
Thank you. We have a few more minutes. Questions?
Yeah, I do have a couple of quick questions. So thanks, Aryya, for the talk. A couple of quick questions. The first one, I really don't know. Every time I hear about poisoning and or federated learning, I see people using the computer vision, and images, data sets, and so on. This is the only case where, or application that this is actually viable. And I haven't seen any data set that is kind of like other than computer vision, or images that people work on, and especially for poisoning and changing patterns and so on. Is there any other application for that?
Yes. Yeah, I think that's a great question. I think that another one that comes to mind very quickly is audio. Right. So I mean, you may not be able to see an object, but you may be able to hear it and identify what it is. Now, obfuscation or camouflage can be done on any type of signal. You just to figure out what type of signals to use to effectively obfuscate the signal that we're trying to hide. And will the same methods work there? I'm not 100% sure, but one of the reasons we're using deep learning as the method or as the technology is because they seem to be quite versatile. Because they are typically because we don't have to necessarily follow a procedural approach to tell of exactly how to remove the noise. It figures it out by itself using some sort of a universal function mapping. So I think that it might be applicable in other types of modalities as well. But we haven't tried any of these, so these are my guesses.
Yeah, it's not just yours. I think every time you see also work work on this, you find that they typically use this video or computer vision type of a data set, and I haven't seen data other than this type of applications. I'm really so to ask you, since you have expertise. The other question I have, which I probably have misunderstood. So the first part of your talk, you were talking about having an IDS to detect if the adversary is already in, right? And you'd like to look at the behavior, looking at the system calls and so on to see if there is some intruder existing in the system or not. Is this actually the goal?
I didn't get the last part, but yes, you're right.
So this actually comes across to me. Well, how this is actually different from, because there are from the IDS perspective, there is people who working on the node level and also, as you pointed out, on the network level. So if the adversary is in to manipulate the communication, then how this is more effective compared by having a network level IDS, and if the adversary is just only try to manipulate the node itself, well, how this is different from just detection of malware, or botnets and others.
Yeah, I mean, so malware detection, I mean, the predominant method is by using signatures. So you take a cryptographic hash of the malware and see if it matches with any of the known malware signatures. These may be malware, but these may not be just malware. The problem is that, so there is some work that is actually being done within the same ArtIAMAS CA, particularly by Rajiv Bora, who is saying that a system call can actually be detected as a potential problem, just an individual system call. And if you do so, then everything that has happened before, using some sort of a tree structure, all the transactions are also potentially anomalous or malicious, and so you isolate them. The problem is that, and there are pros and cons to both approaches, but what we are saying is that a system call by itself may not be anomalous, may not be a problem. But if you look at it in conjunction with what is happening before and after, which is a trace, then you might be able to look at the actual intent of the program that is executing and trying to really get access or make unauthorized changes and things like that. So so we actually, the way I haven't gotten the details in my presentation of that. The way we are looking at it is like a sequence, right? Analyze a sequence. Now, this may have some similarities with language-based models. However, there's also some difference because when we tried to use, and I'm expanding my answer a little bit here, so I might be digressing just a bit. If you use LSTM models, for example, they will not work so well. So we use essentially a one-dimensional CNN, 1D CNN. And that seems to work pretty well. Now, the extent to which one can hide their intentions is an open question. We really don't know. We don't know yet. So it is still an ongoing research. We don't have answers to all the questions, but we are treating the system calls and the traces as a sequence and trying to figure out if a sequence can be identified as a potentially malicious one.
I see. So are you dealing here with zero-day attack, or I
Yes.
assume?
Yes. Even I think, although we haven't really tried it on a zero-day attack, but even if it's a zero-day attack, it will have some system calls, some commands that overlap with other types of executions. So because even a zero-day attack is not 100% new, right? It has to have something, similarities. So I think that is one of our contributions, in the sense to say that if I have built n models, which one is the most likely one to be able to detect, classify a new attack or a new trace or a new application as a malicious or not. Because in other cases, what they do is they say that they presume, at least presumably, there's only one model, source model. But in reality, you can have multiple source models. Right? But we need to figure out which one is the most appropriate one to use. So that is also something that is new. I haven't seen in the literature.
I see. Thank you.
Thank you. Any other questions? We might have time to take one more question. Any questions from anyone else?
Just a request, maybe you could provide a link for where the papers about the talk and so on for anyone who wanted to, kind of like get a bit more details.
Okay, I'll share the presentation, and Aryya probably could share some papers with the group as well.
Thank you.
So maybe I will ask one last question, Aryya. We have 2 minutes. So the first part of your talk was kind of domain adaptation, then you moved to kind of federated learning. Do you have any thoughts how we could combine maybe domain adaptation with federated learning based approach?
That's an interesting idea.
Yeah.
Interesting idea that I haven't thought about yet. But yeah, I mean, I think it's possible. But we haven't really looked into, because the way we have looked, in some ways, these are, so far at least in our research, disjoint problems. And part of the reason is that we are looking at different tiers of the architecture. But yes, I mean, they can be combined. I don't see any reason why, although we haven't really tried anything to say definitively.
Okay. Sounds good. Any other last question, thoughts, comments, any feedback? Okay, if not, thank you. Thank you, Aryya, for the excellent talk. And we would like to thank you from the ArtIAMAS PI team for coming and giving this seminar.
Thanks so much.